is kind of, again, put together a PowerPoint, which hopefully helps you with answering the questions for your pre-lab and post-lab. So what we will do is get started with some basics. It's going to be structural. We're going to start with the structural and electronic differences, and that's going to logically lead us into the different reactions. So today's experiment deals with different chemical tests that can be used to distinguish aldehydes and ketones. So chemical tests are typically ones that, show you the four indicators of a reaction. The first one being a permanent color change, then maybe a temperature change that you can identify using a thermometer, a gas evolution, which you can see with bubbling or effervescence, and then a precipitate formation accompanied by a color change. These are some things that are very easily, perceived by our senses, and that's pretty much the foundation of chemical tests. So when we look at the structure of aldehydes and ketones, this should flow in very easily for you. The aldehydes have a free hydrogen here. So they have a hydrogen directly connected to the carbonyl carbon. Whereas the ketones are fully substituted. The carbonyl carbon here is substituted on both sides. The R and the R prime can be a variety of different groups, ranging from alkyl all the way to alkynyl, which means it can also be triple bonded. The electronic effect is the alkyl groups typically, they are electron donating groups. You could very well have electron withdrawing groups. I'm not saying the R groups always have to be electron donating, but assuming they're electron donating, it's going to reduce the delta plus on the carbonyl carbon. Whereas the hydrogen does not have any hydrogen, any electrons to donate. So it is not an electron donating group. You have only one electron donating group. This is, of course, based on the assumption that the R group is electron donating. If that is the case, you can see that the nucleophilicity of the carbonyl carbon on the ketone group reduces, whereas the nucleophilicity on the carbonyl group on the aldehyde is not, which makes the aldehydes more reactive than ketones. We have to be careful with our statement here. This is really based on the fact that the R and the R prime are electron donating groups. If the electron withdrawing groups, that's a little bit of a difference because you'll have two electron withdrawing groups on the ketone and you can make it more reactive. Okay, so this is really based on the fact that those R groups pump in electrons, dropping the delta plus on the carbonyl carbon. Now you have a nucleophile that's going to attack the carbonyl carbon, okay? Of course, this carbon is flat, it's planar, there's not much of a steric effect. But if these R groups are really bulky, then a steric effect can come into play. For that reason, again, aldehydes are going to be more reactive than ketones because the hydrogen is such a small molecule, such a small atom. At least on one side of the carbonyl, you don't have the steric effect. The reason I started off my PowerPoint with this is the electronic and the steric effects cause all the difference in the reactivity between aldehydes and ketones. Some reactions just occur faster with the aldehydes and ketones. Some reactions don't occur with the ketones at all. What that means is it's really slow and there's no discernible chemical difference that you see right away. You don't see those four indicators of a chemical reaction in a reasonable amount of time. And that's what's going to help distinguish the aldehydes and the ketones. What is it that's going to help us distinguish is aldehydes are just more reactive than ketones. So the reaction can occur faster with aldehydes. So you could start your timer. The one that reacts faster is the aldehyde. And sometimes the reaction may not even occur with the ketones. So a positive test will indicate an aldehyde, a negative test is for a ketone. So with that in mind, we start with our first test, which is called the 2,4-DNP test. DNP stands for dinitrophenylhydrazine, which is this particular molecule. What happens here is a condensation reaction, which is actually something that we're going to study, much later, but this is a condensation reaction with an aldehyde. So what happens is the oxygen reacts with the two hydrogens, and there's an elimination of water, and then the double bond gets connected to the nitrogen. So it is this nitrogen. If I say that's N1, that is your N1 nitrogen. This is your N2 nitrogen right here. So it's the N1 nitrogen that reacts, and the final product is called 2,4-dinitrophenylhydrazone. That is the reaction. The reaction leads to the formation of the hydrazone, which is usually a red-orange shiny precipitate. Now, what's important is the reaction is positive for the aldehydes. It's positive for the ketones. So it is not a distinguishing reaction. It is positive for aldehydes and ketones. So it's a common reaction for aldehydes and ketones. The difference in reactivity is not so great, so you cannot use a timer to distinguish these reactions. So if you get a positive test, that just tells you the carbonyl is either an aldehyde or a ketone. I'm not going to belittle the test. It is an important test because it's a negative test for all other carbonyls. So if you don't get a positive test and there is a possibility of a carbonyl, that means it's an ester, carboxylic acid, as an anhydride. All those carbonyls are going to give you a negative test. If you get a positive test, then you know your carbonyl is aldehyde or ketone. So it is quite an important test, a nice red-orange precipitate that you can miss. Our next chemical test is a chromic acid test. Feel free to stop me at any time you have any questions. Okay. So our next test is a chromic acid test. It is a positive test for primary and secondary alcohols. The reason I pointed that out is it's not new information for us. We know a little bit about this test. It is a positive test for primary alcohols and a positive test for secondary alcohols. It's a negative test for tertiary alcohols. It is a positive test for aldehydes. It's a negative test for ketones. So it is a distinguishing test for aldehydes and ketones. Okay, so let's take a look at what this test is. So what you're going to do is what you see here is a primary alcohol. This is really given for comparison. What you really are interested in is an aldehyde. So you take chromic acid, or you can take it in many different forms, which you know. Potassium dichromate, sulfuric acid will work just fine. Chromium oxide, sulfuric acid works just fine. H2CrO4, which is chromic acid, works fine. All of this plus heat. So it's a pretty harsh reaction. In all of them, chromium is going to be +6. So chromium is the oxidizing agent. It's going to oxidize a primary alcohol into an aldehyde. But if you start with an aldehyde will become a carboxylic acid. If you start with a primary alcohol, the aldehyde will eventually become a carboxylic acid. So chromium is the oxidizing agent. So chromium 6 plus gets reduced to chromium 3 plus. The color of chromium 6 plus is orange. The chromium 3 plus is green. So positive test is the change from orange to green. This reaction is also called the Jones test. It is a test that's commonly used for the DUI by the cops, where if you're asked to breathe into the breath analyzer, the orange color turns green. It shows that the blood alcohol concentration is above the legal limit. So that is where the chromium 6 plus becomes chromium 3 plus. It's an important test because it's a distinguishing test for aldehydes and ketones. Ketones, the color will persist, which means the orange color stays orange, no change. The third test is a tolerance test. Tolerance test is a distinguishing test for aldehydes and ketones. So it's another great test. It'll give you a positive test for aldehydes. The positive test is a function of a silver mirror. I say mirror because when you do it in a round bottom fast or in a test tube, it coats the inside walls of the glassware and forms a shiny mirror. The reaction involves silver, ammonium hydroxide, sodium hydroxide. It's a mix of everything. This is called a tolerance reagent. It's nothing but a strong oxidizing agent. The strong oxidizing agent converts aldehyde into carboxylic acid. The side product is what really gives us the test. The side product is silver, and silver precipitates as a shiny mirror and coats the inside walls. So if you get a positive test, it's an aldehyde. Negative test is ketones. The last test we have here is the iodoform test. It's a positive test for methyl ketones. So it has to be a special type of ketone. One side of the carbonyl should be a methyl group. The positive test is a formation of a yellow precipitate. The yellow precipitate is iodoform. So you'll add iodine. The combination is iodine and sodium hydroxide, both added in excess. This is your iodoform, CHI3, which is the yellow precipitate. This is a reaction we studied where the methyl ketone becomes a carboxylate salt. Okay. So we have some tests that will be positive for both aldehydes and ketones, 2,4-DNP. Chromic acid, distinguishing test for aldehydes and ketones, same. Tolerance, a very characteristic test specifically for methyl ketones. So what I want to do is take a quick look at the pre-lab questions, just kind of go over them, and then I'll look at the post-lab, and then we'll look at what your unknown is, and that should help you finish the lab flow, okay? What is a functional group that determines if a compound is an aldehyde or ketone? So the functional group we are looking at is the carbonyl. So carbonyl group is the general name of the functional group. Of course, if you have a hydrogen directly attached, it's aldehyde. If not, it's a ketone. So what observation is expected for a positive iodoform test? The observation, as I've repeatedly told you, is very important, is a yellow precipitate. For the positive tolerance test, we are expecting a shiny silver mirror coating on the inside walls of the glass. So we're really not looking for an organic compound here, it's just the silver, okay? You want to write an equation for the tolerance reagent. I would keep it kind of general, or you can take a specific example. You're going to have silver, ammonium hydroxide, sodium hydroxide, and you want to gently heat it. You are going to get the ammonium salt of this acid, but the key thing is you can have a downward arrow. That's your silver mirror. The last question, why aldehydes and ketones have a higher boiling point. So I'm going to put the aldehydes and ketones together here. Then the corresponding hydrocarbons, I'm just going to say R prime for the hydrocarbons. They both have dispersion forces. So that's common for both. I'll write dispersion forces. They both have, this one has dipole force. Here the dipole force, no hydrogen bonding in both. Okay, so it's a presence of the dipole force. You have more intermolecular forces of attraction, and therefore it's going to have a higher boiling point. Anytime you're asked to comment on a physical property such as boiling point, melting point, water solubility, viscosity, surface tension, go back to your basics, go back to your IMFs. As you work through this, did you have any questions? So I think I made this due the same day the lab is due. You may want to check. If that's not the case, I'll make this due next Monday. And I can fix that, okay? Now this, everybody gets the same unknown code. You're told that your compound is slightly soluble. 2,4-DNP, it does give a positive test, which means it's an aldehyde or ketone. Chromic acid, it does give a positive test, so you have to find out whether it's an aldehyde or ketone. Tolerance gives you a positive test. Iodoform does not give you a positive test, okay? With these in mind, you're going to complete these questions here. They're fairly straightforward. I'll just give you a little bit of idea here. Solubility tests acetone. So acetone is going to be completely soluble in water. When you get to benzaldehyde, the reason why acetone is going to be soluble in water, so just a quick look here, is because of the hydrogen bonding. Because as I said, you want to connect to the intermolecular forces. Yes, you're going to have hydrogen bonding in benzaldehyde, but you got a pretty heavy hydrocarbon chain. So the most I can expect here is sparingly soluble. If you write insoluble, that's totally okay. Same thing with the butanol. You're going to have a pretty big, hydrocarbon chain. So if your hydrocarbon chain is going to increase, don't expect solubility. See, with cyclohexanone, you got a pretty big hydrocarbon chain. So anytime your hydrocarbon chain is somewhat big, the solubility is definitely going to drop. So that's what you want to keep in mind as you predict the solubility. Unknown itself is given to you here, so it's slightly soluble, so you want to write that down. 2,4-DNP, in each case, you want to predict it. It's a positive test for both aldehydes and ketones. So your observation is a red-orange precipitate. Okay, you want to give the name of the precipitate and say it's a positive test for carbonate. Chromic acid is a positive test for aldehydes. Okay. It is a negative test for ketones. The positive test in chromic acid is an orange color solution turning into, it's kind of like a dirty green precipitate. It's not like a nice, beautiful leaf green or dark green. It's kind of like a brownish green. There's a brown tinge to that green. Tolerance test, positive for aldehydes, negative for ketones. Positive test is a formation of a silver mirror. It'll coat the inside walls, okay? Iodoform, positive test for methyl ketones. Everything else is negative, so it's negative test for all other types of ketones and negative test for all aldehydes. Your positive test is going to be the formation of a yellow precipitate. So based on all the information you gathered from the test, you want to comment on your unknown. Okay, and what kind of unknown is it? Whether it's an aldehyde or a ketone. If it's a ketone, you want to say whether it's a methyl ketone or not. Then here, these questions should all stem very easily from the pre-lab lecture. What tests distinguish your unknown compound as an aldehyde and ketone? Keep in mind your distinguishing tests are chromic acid tests, right? Then you got your tolerance test. Then you got your iodoform test. These are your distinguishing tests for aldehydes and ketones. How certain are you? Don't just say yes or no. Please provide a reason here. Okay, provide a rationale as to why you think it's an aldehyde or a ketone. Okay. If you compare your unknown compound to the tested known compounds, you're actually asked to guess what your unknown is. So your tested compounds are all given here. Acetone, benzaldehyde, butanol, cyclohexanone, okay? So your unknown should be one of those four. So you want to come up with the actual name of the unknown there. So fairly straightforward lab. I think you should be able to handle this well. So please take a moment, look at your lab flow. I actually just screen captured the lab flow questions, so I won't pull the lab flow out for you here. Let me know if you have any questions. Okay, one other thing that we have here is going to be our Spartan. So I'll share my screen pretty quickly here. Pull those things out. So you want to go to I believe this is your last Spartan lesson for the semester. Take a quick look at it. This is going to be on nucleophilic acyl substitution. And you have a variety of compounds given here. So I'm going to bring it back on the screen. Just a second. So this is lesson 7. So carboxylic acids have different reactivities. It's not some new information for us. We already know this. We know some carboxylic acids that react faster, carboxylic acid derivatives that react faster than others. So here are a series of them that are given: acetaldehyde, acetone, acetic acid, methyl acetate, acetyl chloride. There's a typo here. I'll fix it. Acetic anhydride and N dimethyl acetamide. The first thing I would like you to do is get the structures of these compounds. So I have these written here. So let me go ahead and we will work on the structures. So acetaldehyde, we will start. I'll just give them some numbers here so you can relate to the legend. So the first one, acetaldehyde, is a common name. So you may want to write down the structure. That's acetaldehyde. Acetone is a pretty common chemical. Then we have acetic acid. These are all common names. We have methyl acetate. So you do need the structures first. Then we have acetyl chloride. Any questions? I'll follow the chat, so go ahead and let me know. Acidic anhydride. We're keeping it very simple with a methyl group. That's the whole thing. And then we have acetamide, but this is an NN dimethyl. So this is actually, you got nitrogen connected to 3 groups. The next thing we want to do is go ahead and find out what kind of compounds these are in terms of functional groups. This is aldehyde, ketone, right? You know these things well. This is carboxylic acid. So I'm just going to go ahead and write the functional groups of these different compounds. And then the last one here is an amide, but I'll go ahead and write it as a tertiary amide because the nitrogen is connected to 3 carbons. So we got a variety of compounds here, and they all don't react with a nucleophile at the same rate. So the question is, if I brought in a nucleophile, are they going to attack these carbonyl groups, at equal rate? Obviously not. They're not going to do that. And we want to see why. So let's go ahead and take a look at the question here. So does this guarantee that they will be as reactive towards nucleophiles as normal carbonyl compounds, which are aldehydes and ketones? One way to do this is to get the energy of the LUMO. You have done this a few times, lowest energy molecular orbital, and that is where the nucleophile is going to dump electrons. So I was asked a question as to what this actually means to students who actually just met with me. So you're going to have a lot of molecular orbitals in each of these molecules, and they're going to have electrons. The one that is filled and is the highest in energy is called the highest energy molecular orbital. And then the one that is not filled and the least in energy among the ones that is not filled is called the lowest unoccupied molecular orbital. Now, when the nucleophile comes in, it brings a lone pair. It's not going to put it in an orbital that's occupied. It's going to put it in the LUMO, okay? So the question is, does the LUMO play a role? So the lower the LUMO is, it's more easily accessible to the nucleophilic attack. So we want to come up with the LUMOs for all these molecules. So this is what I want to show you here. You want to open Spartan. So open a new file. And the first thing you want to do is build an aldehyde. So this is what you're going to do. Okay? So this will be your aldehyde. If you take a look, you got your first aldehyde built there. So I file, and then the second molecule, remember to go to build new molecule and go to the next one. So next one is going to be your ketone. So we'll have the next one built, right? So now you can see that you got a ketone built. So you're going to build all these molecules and then go to display spreadsheet, okay? And then you can just select this and go ahead and write the names of the aldehydes. So the first one was acetaldehyde. So we're going to do that. The second one, you just select that and you're going to write the name of the ketone. So you'll have a series of 7 molecules built. Once you're done with that, I want you to go to add, and there is your LUMO energy. Just select that, and that's it. Okay, it'll appear in the spreadsheet. Then go to display spreadsheet. You already have that opened up. So what you want to do is bring both molecules on the screen and make sure that they're not coupled so you can move them independently. And the way I added this is I go to add and just select E-LUMO. That is the energy of the LUMO. Okay. Next, you go to set up calculations, go to equilibrium geometry, then go to PM3, everyone, because I'll just do it in 2 seconds. Submit, and then you can call this lesson 9 or whatever. Save it. It shouldn't take too much time, and you see that coming up. Okay, so you will get all your energies of the aldehydes, ketones, and so on, and you're just going to arrange it. That's all you need to do. You're going to display the LUMOS, which the lowest, which carbon has the highest energy. The base LUMO energy you're going to arrange. The most important statement is the molecule whose LUMO is going to be the least is going to be the most Everybody get that? The one, the least LUMO is going to be the most reactive, and then make a comment on whether your results consistent with what you observe. And then we can log off at that time. If you have any questions, please stay back. So any questions so far with any of this? Okay, I'm